Welcome back to another video. We're going to be going through 2024 Jan, question number 12 and question number 14. Okay, so question number 12 says, a circuit contains a filament bulb when the potential difference across the filament is 8.9 volts. The resistance of the filament is 7.5 ohms. Calculate the time taken for a charge of 5 coulomb to flow past a point in the filament. So we know the current is equals to the change in charge over the change in time. So we need to first find the current. We know the charge, and then from that we can find the time taken. So we know V is equals to IR. So V over R is equals to I. So 8.9 over 7.5. That gives me 1.186 amps. So 1.186 amps. Let me remove the amps from there. I don't think we need that. Equals to 5.0 and the time t. So time t is equals to 5 over 1.186. That's going to get me 4.2 seconds. We're going to be looking at question number 14. It says a student investigated the EMF and internal resistance of a battery. And then it says the student connected a high resistance voltmeter across the battery. The battery was not connected to any other components. Explain why the reading on the voltmeter gave the EMF of the battery. So our setup looks something like this. And then we have the voltmeter here as well. Okay. Now using Kirchhoff's law, I can make the equation. So sum of the EMF is equal to the sum of the potential difference. So EMF, there is the battery. So E is equals to the internal resistance, the potential difference lost to the internal resistance. I'm going to write that as I and small r. And then you have the potential difference across the voltmeter. Okay. Now what's going to happen is the voltmeter has really high resistance, really high resistance. And because of this, the current in this circuit will be approximately equals to 0. And because of this, what will happen is that E is equals to, now I is approximately equals to 0, so we're going to write 0 times R plus V voltmeter, right? And because of this, we can say that this is negligible, so we can cancel it out, right? Because the current is approximately 0, so the potential difference that's lost due to the internal resistance is also 0. So the EMF of the battery is just equal to the potential difference across the voltmeter. Okay, so I hope that makes sense. This is why the reading on the voltmeter gave the EMF of the battery. So your answer is going to be the voltmeter has very high resistance, so the current drawn out is negligible. I is approximately 0. The lost volts due to the internal resistance is negligible, so there is no PD across the internal resistance. So what's going to happen here, again, I'm going to draw the same diagram. Right, so the current drawn out will be approximately 0. E is equals to IR plus V voltmeter. Now this is called the lost volts. So this is negligible because the current is negligible, so it's approximately 0. So this is also approximately 0. So E is equals to V voltmeter, right? And the resistance of the voltmeter is so high that the EMF of the battery is going to be given by the reading on the voltmeter. Okay, so that's going to be the answer to part A. Let's move to part B. It says the student investigated how the potential difference V across the battery varied with current I in the battery. Draw a circuit diagram for this investigation. So the diagram is going to look something like this. We've got the battery, internal resistance, the voltmeter connected in parallel, ammeter is connected in series. We've got the variable resistor here, so that we can change the resistance of it, and then we can vary the current and potential difference in the circuit. And then what we can do is we can plot a graph, which we did in the part C. Okay. C says the student plotted her results on the graph as shown. Determine the EMF and the internal resistance of the battery. So we're going to get an equation using Kirchhoff's voltage law as the sum of the EMF is equals to the sum of the potential difference. So the EMF of the battery is equals to IR, potential difference across the internal resistance, plus the potential difference across the resistor that we had in our circuit. Okay, so now what we can do is we can rearrange this equation. And one of the things, let me point out before, is that the reading on the voltmeter will basically give us the potential difference across this resistor, right? Because let's say this is 8 volts, right? And our internal resistance is going to take 2 volts. So it's going to start here at 8 volts, and then your current will move and it will come right over here, right? And right over here. So 6 volts will be taken by the resistor, and then the rest of the 2 volts will be taken by the internal resistance. So the potential difference across these 2 points that the voltmeter will measure will be 6 volts. Okay, so basically the voltmeter has given us the potential difference across the resistor, so keep that in mind. Okay, so that's why I wrote V resistor there. Okay, now coming back to the question, I'm going to rearrange the equation. So I'm going to write V resistor is equals to Ri minus E. I'm going to write Y is equals to Mx plus C. So the internal resistance is the gradient of the graph, and the y-intercept is the EMF. So y-intercept, we can see here that's going to be 8.2468. So 8.8 volts. Now we're going to calculate the internal resistance. So that's going to be, you're going to take 2 points here. Let's go with this point. And then the other one, let's go with this point. So the 2 points we're going to get as 0.6 and 7.4 and 2.7 and 2.6. Now we can use the formula y2 minus y1 over x2 minus x1. Plug the points in the formula and let's get the value of the gradient. So we're going to get the answer as minus 2.28 ohms. So that's going to be the gradient. And now we're going to write the answers down. So 8.8 volts, and we can write this as 2.3 ohms. Okay, in part II, it says explain why there's a maximum current that can be supplied by the battery. So for this, we're going to look at a circuit diagram here. So we've got the battery, the internal resistance, and we've got the external resistance, which is the resistance of the variable resistor. So I'm going to write the equation here. So E is equals to IR plus VR. Now what I'm going to do is I'm going to decrease the resistance of our variable resistor. And as I'm going to decrease it, the current will increase. So I'm going to decrease the resistance of this. And as I do this, the current in the circuit will increase. Now, I will reach a point where I will decrease my resistance, the external resistance, to 0, right? So at this point, our potential difference across the variable resistor will be equals to 0, so it will get cancelled out. And our EMF will just be equals to the current times the resistance of the internal resistance. And this is when the current will be maximum. Basically when your circuit is shorted. So we call this short circuit. That's when you will have the max current, when the potential difference across the internal resistance is equal to the EMF of the battery. So your answer is going to be that as the current increases, the PD across the internal resistance increases, more voltage is lost internally. Until the external resistance of the circuit is 0, all of the voltage is lost due to the internal resistance. PD across internal resistance is equal to EMF. This is when the current is maximum and can no longer increase. So that's going to be your answer. Basically, this is going to be, as we said, short circuit, and your external resistance will be equals to 0. Right now, I'm going to show you paragraph from a textbook explaining the same concept so you can get more clarity. So I want you to read that slide, and after that you will see the MS and ER.